Everybody participating in this presentation, Coarse Geometry and Index Theory, both my friends here at Penn State, who I can see in the lecture room, and my friends in Germany, some of whom I can recognize and pick out. Hi, Thomas. And some I cannot. This is by nature of an experiment. So the first thing that I need to do is to say thank you very much indeed to the technical people, to Micah and Philip, who have made this experiment possible. The reason that, the sort of most immediate reason that I'm giving this lecture in this slightly different way is that for health reasons I'm unable to travel at the moment. But I just wanted to take 2 minutes to say to you that also by giving a lecture in this kind of way, I am saving approximately a ton of carbon dioxide emissions poured into the atmosphere, flying me from here to Germany and back. As you all know, the Earth is full of carbon, and our people, humankind, have been burning it for a long time. As a result, the concentration of carbon dioxide in the atmosphere has increased, and just recently went through 400 parts per million, which is a level it never had reached for the last several million years. It's expected that that has a big effect on the climate, and it's likely, nay, certain, that we are going to have to change our behavior drastically. One of the things about mathematics is that we should understand the difference between y and dy by dx. The quantity of carbon in the atmosphere is y. At any rate, by not traveling to Germany, I'm reducing dy by dx a little bit. I would encourage you young people, as you see this technology, this is just getting started. It's a bit glitchy in places, but we're going to have to learn to collaborate in ways which don't involve pouring more carbon into the atmosphere. If we want to keep going with the world as it is, that's how we're going to have to change. So take a look. I think there is a great prospect in running academic life with less travel, with flying less. And that's what we're trying to do in this talk. So I feel kind of inspired that this is a model for a way which may develop of collaborating, as well as a fun time for me to share some mathematics with two audiences at once. So let's get on with the mathematics. My task is to tell you about coarse geometry and index theory. And today's lecture is an introduction. I'm going to have 3 parts. First of all, I'm going to remind you a little bit about how the classical theory of the index works. The theory which was developed by Atiyah and Singer in the 1960s. Then I'm going to open the question, well, what about what happens when we take that theory and try to move it out of the world of ordinary compact manifolds where it normally lives into the world of non-compact manifolds. As you will find, there are several possible answers to that question. The one I gave is related to coarse or large-scale geometry, so I'm going to explain what that is and how it ties up with index theory. And then at the end of the talk, if we have time, we're going to do an example to show that this whole discussion has some content and is not just playing around with empty symbols. So that's the plan. If anybody has any questions, those of you who are here at Penn State can just ask questions in the ordinary way that you would ask questions. But those of you who are in Germany, I think the idea is that you will ask your question and somebody, the moderator in Germany, that would be Philip, right, is going to raise a hand, send a signal to Micah here at this end. Micah is going to yell at me and tell me to shut up, and then you are going to be able to ask your question. So that is not the highest technology available, perhaps, but that's the way we're going to do it. So please feel free to ask questions, whichever end of the process you're on, and we'll do our best to answer them. Okay, so let's talk about index theory. In the world of index theory, one is interested in differential or perhaps pseudo-differential operators acting on sections of a vector bundle over a manifold. I'm going to stick to first-order differential operators because I want to keep everything simple. And we will mostly assume that everything in sight has an appropriate metric. So D is a, S is a vector bundle. So you see this little hand here. That vector bundle S, we can assume has a Hermitian metric, a complex inner product. And the manifold M, we'll assume it has a Riemannian metric. And once we have metrics around, it's appropriate to talk about self-adjointness. And we'll assume that D is formally self-adjoint or symmetric, as it's also sometimes called. Now, if we have any kind of differential operator, first-order differential operator, the symbol of D is by definition the correction term which makes the Leibniz rule for a product work. Okay, so if you apply the operator D to a product, function F times section S, so the natural thing to guess, if you were wrong, would be that would be F times D of S, but as we all know very well, there's a correction term involving the derivatives of F, and that correction term is a symbol of the operator, sigma sub D, that's what we'll call it, and it's applied to dF, the exterior derivative of F, which is a 1 form. So this formula is both the definition of the symbol, if you like, and it's also the Leibniz rule for these kind of first-order operators. And the definition of an elliptic operator is that D is elliptic if the symbol, sigma D x of psi, so that's actually an endomorphism of the fiber of the bundle at x. D is elliptic if this endomorphism is an invertible endomorphism for all non-zero values of this cotangent vector psi. Now, the reason this is important is that the symbol governs what you might call the first-order behavior of the operator. So that if the symbol is invertible, what that means is that the operator is invertible kind of to first order, whatever that turns out to mean. And elliptic operators are ones which are invertible, quote, to first order, or up to some error term. Typically, the error term turns out to be smoothing operators, operators which, whatever you put in, a smooth function comes out. All right, so that's the definition of ellipticity. And I need to say a few words, hopefully as few as possible, about the notion of grading. There are some standard examples of elliptic operators, which are the Dirac operators, which I would guess have probably already been mentioned in your conference and will be mentioned many times a day until the conference is over. And these tend to have an additional algebraic property, at least in the case of the base manifold M being even dimensional. This property is called a grading. Okay, and what goes on with a grading is that the bundle S comes equipped with a direct sum decomposition, as I've shown there, into two pieces, S plus and S minus, and the operator D maps sections of one piece to sections of another piece. Or if you like to write it out in terms of matrices, the operator D looks like this. It's a 2 by 2 matrix. It has zeros down the diagonal, and here is a place D plus. The operator D plus maps sections of S minus to S plus. Here's D minus mapping sections of S plus to S minus. So this structure, which the geometry tends to give you in the even dimensional case, is called a grading on the pair D comma S. And there are also more elaborate notions of grading as well, which involve Clifford algebras, basically more involutions acting, not just one. These are important, especially in geometric examples when one considers what are called real structures, but I won't go into the details of those. Okay, so we have operators, we have gradings. The point about operators is to do some analysis, so let's talk about the analytic consequences of ellipticity. Okay, here's the key thing. If D, as defined above, is elliptic, and the pair consisting of M and D is complete, I'll say in a moment a couple of words about what we mean by that, then D is in fact an essentially self-adjoint operator on the Hilbert space H, and for all rapidly decaying functions f, this bounded operator f of D is a smoothing operator. So let me just call to your mind some of what's going on here. So if we, in the spirit of very simple linear algebra, think of D as a diagonal matrix with eigenvalues down the diagonal, which of course is far too simple-minded in the infinite dimensional case, but it gives us an idea what's going on, then there's a process whereby one can define what we mean by f of D for any function, reasonable function f defined on the spectrum, and that's just the diagonal matrix with f of lambda 1, f of lambda 2, and so on, same things down the diagonal again. This process is called the functional calculus for the operator D. And especially when we're dealing with unbounded operators like differential operators, functional calculus is a kind of tricky process. It requires a technical notion, essential self-adjointness for the operator D in order to be well defined. And what I'm saying in this proposition is, first of all, that if we have this notion of completeness, then indeed the functional calculus is well defined. And secondly, that the output of the functional calculus, the spectrum of a self-adjoint operator is real, so f is a function on the real line. As long as f's rapidly decaying, that means that it decreases faster than any polynomial, then the output of the functional calculus is a smoothing operator. Remember, I told you what that is. That's an operator which, whatever kind of thing you put in, even if it has singularities, the output is always a smooth function. And I remark here in this paragraph, there's a general notion of completeness which is appropriate here. You can read about it in Nigel and my book, Analytic K-Homology. But for Dirac type operators, which are the ones we're interested in mostly, it actually turns out to be equivalent to talking about completeness of the Riemannian metric on M in the usual sense of Riemannian geometry. I see a question, yes?
So what if D is not first order?
What if D is not first order? So the question was, what if D is not first order? The answer is, I am not talking about it in that case. I mean, there are many ways in which I can generalize the discussion here, but I want to keep it simple, and this is one way to do that. So the first order condition is not at all some kind of vitally necessary condition. It's just a consequence of my natural laziness.
Well, no, I think it's much more than that. I mean, I think it's a fact of life that the most interesting examples, the examples that anybody would study at first to get started, and they are very interesting examples. They're all first-order Dirac type operators.
Yeah.
Those are the heart of the subject group. So it isn't just John's somewhat dictatorial mapping here. It also has to do with what are the basic examples in the subject.
Yeah, as a consequence of my natural laziness, that I want to study the basic examples first. So there I can get both of us in. Okay, so a corollary is this. I didn't say whether the manifold M is compact or not. Remember, a complete manifold does not have to be compact. But if M is compact, then f of d, this thing on the previous page, is a smoothing operator on a compact manifold. And a smoothing operator on a compact manifold is, in fact, a compact operator in the sense of Hilbert space operators. Okay? So it follows that if M is compact, then the kernel of the operator D is a space consisting of smooth sections, and it's finite dimensional. Okay, why? Well, let's consider the identity map from the kernel of D to itself. Okay, that's a function of D. We could think of it as being basically any reasonable function which is equal to 1 at 0 and 0 out near infinity in the real life. That would be the identity on the kernel of D, and that's clearly a rapidly decaying function. So the identity map from the kernel of D to itself is a smoothing operator, therefore a compact operator, as I mentioned, and the identity operator on some Hilbert space is compact if and only if that space is finite dimensional. So the kernel of D, being a Hilbert space on which the identity is compact, is a finite dimensional space, and since the identity is also a smoothing operator, it's a finite dimensional space of smooth functions. So this is the classical case for index theory. You've got a compact manifold, the kernel is finite dimensional, it consists of smooth sections. What's more, if we have this additional structure of a grading that I mentioned before, the even dimensional case, so S decomposes as S plus S minus. The kernel of D, which is equal to the kernel of D squared, also decomposes as a direct sum to a positive and a negative part, just simple linear algebra, that is. So we have two finite dimensional pieces. The positive part of the kernel is a finite dimensional vector space. The negative part of the kernel is a finite dimensional vector space. We've got two dimensions. We take the difference of those dimensions, we get an integer. That integer is what is classically called the index of D. And this index, why should we do that? Why should we, for instance, take the difference of those two dimensions rather than adding them up? This index is a topological invariant of the operator. It remains unchanged if we vary the operator in the space of elliptic operators. Okay, so whenever something is a topological invariant, that's telling us that it's important. That's telling us to pay attention. If something is not a topological invariant, if it just jumps wildly around whenever we perturb anything a tiny bit, maybe we shouldn't pay so much attention to it. But a topological invariant, something which remains the same when we change the operator, that's pointed to some kind of essential property. This is like we're looking into the soul of the operator here and seeing what we got. So this is a significant property of the operator. So the index is a homotopy invariant. In other words, it remains constant as D is varied in the space of elliptic operators. A proof can be based on the so-called McKean-Singer formula. I mean, there are several proofs, but here is one. The McKean-Singer formula tells you that the index is equal to the trace, or rather the supertrace, parenthesis. Supertrace means trace on the positive graded part minus the trace on the negative graded part of f of d squared for any reasonable f with f of 0 equal to 1. Now, why does this formula prove that the index is a homotopy invariant? Well, because standard results on the functional calculus are going to tell you that this expression, supertrace of f of d squared, is a continuous function of the operator d. As we vary d continuously, this expression is going to vary continuously as well. Okay, so it's a continuous function. On the other hand, it's an integer because it's the index of something. And everybody knows that continuously varying integer valued functions are constant. Now, that's why the McKean-Singer formula implies the homotopy invariance of the index. So why is the McKean-Singer formula true? Well, I'm going to try and draw a picture which may or may not successfully show you why the McKean-Singer formula is true. So I want you to think of the operator d squared. So remember, because of the grading, this splits into two parts, d plus, d minus, and d minus, d plus, the positive and negatively graded parts of the Laplacian, the d squared operator. And those two parts, each of them have a spectrum. They have some zero eigenvalues, call that lambda 0. That's the kernel, of course. That's what we're interested in when we're looking at the index. Then they have eigenvalue lambda 1, and lambda 2, and lambda 3, and so on. And d minus d plus similarly has its own spectrum, lambda 0 prime, lambda 1 prime, lambda 2 prime, whatever. Okay, and you'll notice that I drew those underneath each other exactly. That's not actually an accident, because if you think about it, it's a fact of linear algebra that the non-zero eigenvalues of a product of operators, a times b and b times a, occur in exactly the same places and with exactly the same multiplicity. Okay, now if you look at this supertrace expression, well, f of d squared, I already showed you the sort of naive idea of what we mean by f of an operator. It's just something built from the eigenvalues. If you just write down that supertrace expression in the naive sense and look at the contributions from the various eigenvalues, looking at d plus, d minus, and d minus, d plus separately, you'll find that the contributions from all these things with the red arrows cancel out. And all you're left with is the difference of the contributions from lambda 0. That's the index. So that's the proof, very quickly, of the McKean-Singer formula. Let's get rid of that ink. There we go. Last thing I want to say before I move on from the classical index is that there's an interpretation of all of this in terms of K-theory. So let S, fancy S, denote the graded C-star algebra, C0 of R. Graded, again, means that things are divided into odd and even. Here we're looking at functions on R. We know how to divide them into odd and even, right? The odd functions are ones like sine x. And the even ones are the ones like cosine of x, symmetric or anti-symmetric about the origin. That makes them a graded C-star algebra. Let A be any other C-star algebra, maybe graded or not. Let M be a Hilbert module. Let K be the compact endomorphisms of M. Sorry to throw all those things at you at once. And then here's the definition that I want. A cycle for A is just a graded star homomorphism from the algebra S to the compact operators on this module MA. Okay, so there are natural notions of homotopy equivalence and direct sum of cycles, and with a bit of ingenuity that makes a collection of equivalent cycles, classes of cycles, into an abelian group which we can call K of A. This is what Nigel calls the spectral picture of K-theory. It's equivalent to other definitions of K-theory. If we're a bit more ingenious with gradings, Clifford algebras and so on, we can see all the other K-theory groups, Ki of A, by constructions like this as well. So I want to point out that we have, in the discussion we've had, a perfect example of this machinery. A functional calculus for an elliptic operator on a compact manifold, for either case, gives us a homomorphism from S, the algebra C0 of R, to the compact operators on L2 of S, L2 of the vector bundle. That's a Hilbert space, so it's a Hilbert module over the complex numbers. So the data, the functional calculus data for a elliptic operator on a compact manifold gives exactly an element of the K-theory of the complex numbers, K of C. And this element is nothing other than the index. This is a different way of interpreting the index. In fact, somewhere sort of hidden under the hood of all this machinery with the definition of K-theory and so on is the McKean-Singer formula. That's the key to this understanding of the index as a K-theory class. So, summary. A classical index is an integer. That's a difference of dimensions defined for elliptic differential operators on compact even dimensional manifolds. I apologize, I left out the word compact here. That belongs to the classical case. This index is a homotopy invariant. It follows, it depends only on the homotopy class of the symbol, interpreted in some suitable sense. And the Atiyah-Singer index theorem in the early 1960s gave the explicit answer to the question, what is this topological invariant in terms of standard topology, which means or meant characteristic classes. Okay, so that's background. Now, $64,000 question, what happens when M, the manifold on which we are looking, is no longer compact, but is still complete? So it's like the real line or the hyperbolic plane or something more complicated than that. Okay, in that case, f of d is still a smoothing operator, but it's no longer a compact operator. We don't get star homomorphisms from S to the compacts. We don't get an integer index. What is going to happen? So the answer turns out, as is now known, turns out to be that there are lots of different ways of defining index on a non-compact manifold, all of which involve taking account in some structural way of the non-compactness. And there are different ways of doing that. So the way that I'm going to talk about it, and the way this conference is focused, is on ideas of index which take account of the non-compactness by looking at what's called the large scale or coarse structure of the manifold M. So in order to understand that, we need to introduce this object, which some people call the row algebra, or I like to call the translation algebra, of a manifold or a metric space X. Okay, so this is the second section of the talk. We're actually going to set up the coarse index and start by talking about this particular C-star algebra. Any questions? Are there any questions from back over there? All right. So suppose we have a proper metric space. That just means a metric space where closed-bounded sets are compact. We could think of a complete Riemannian manifold, if you like. And H, a Hilbert space that's a module over the functions on X. Okay, so what you should be thinking of is X is a complete manifold. H is the sections of one of these vector bundles S on which elliptic operators are going to operate. Okay, and of course, a module action is multiplication, pointwise multiplication. So suppose we have an operator T acting on this Hilbert space. It would do you no harm to think of the Hilbert space as actually being L2 of X. we're going to say that it's controlled if the condition that you can see here is satisfied. Let me try and draw a picture of this condition rather than, well, I'll talk through it afterwards. But so an operator on X we can think of as being given by a matrix, or if you want to be a little bit more careful and precise, a distributional kernel defined on X cross X. Okay, if you want to map L2 of X to L2 of X, a kernel KXY defined on X cross X is one way of doing it. Okay, inside X cross X, of course, is an important subset, the diagonal set of points, both of whose coordinates are equal. And what this control condition says is that there's a constant r, a distance, r, here it is, such that the kernel or matrix or whatever it is which describes the operator is supported within distance r from the diagonal in X cross X. Okay, it's the definition, the way it's written is kind of backwards definition, but that's what it ends up saying, that the kernel which defines the operator has to be supported within this finite distance from the diagonal. Okay, that's what we mean by controlled operators. They have a finite range of influence even on this infinite space. Okay, so imagine for a moment that the universe was infinite Euclidean space, and we look at the operator which just evolves Maxwell's equations for 1 second. Okay, then that would be a controlled operator, because any light disturbance, any signal that I emit here in 1 second cannot travel further than 186,000 miles. So R is 186,000 miles in that case. And it's easy to see from this picture that controlled operators form an algebra. If I take an operator with propagation, as we say, R, and multiply it by an operator with propagation S, then I get an operator with propagation at most R plus S. So that's our basic definition, the key definition. And then another definition, not quite so important, is that an operator is locally compact if when you cut it down on one side or another by a function, you get a compact operator. This condition encapsulates the basic property of smoothing operators on non-compact manifolds, actually. That's what it's there for. And then, if we take the locally compact, that's this condition I just wrote, and controlled, that's the one on the previous slide, operators, and put them together, they form an algebra. We can take the norm closure on L2 of H, on H, that forms a C-star algebra. We'll call that the translation algebra of X. So that's the algebra consisting or generated by operators which don't propagate more than a uniformly finite distance. Now, why should we be interested in this thing from the point of view of elliptic operator theory? Well, the reason is this theorem, which I'll call the propagation theorem. So suppose we're in the situation that we've been talking about all along with a self-adjoint elliptic operator on the bundle S, and suppose we have basically the completeness condition, finite propagation speed. I did not even say, I should have said that M was complete. Maybe I said it earlier. So suppose we have D self-adjoint and elliptic on the bundle S over M. M is complete. We have finite propagation speed. Then, with all of that stuff, f of D, the functional calculus of D, so remember that was the thing which played the key role in the discussion before of the index. This f of D is not just a smoothing operator. It's an operator that belongs to this translation algebra, C star of M H, for all f in S, that's C star algebra of continuous functions on the real line, vanishing at infinity. Okay, in other words, what am I telling you? I'm telling you that if I look at the functional calculus for an elliptic operator in the situation that I've described, that functional calculus lands up always in C star MH. In other words, it describes what we call a cycle for this algebra, the row algebra, this C star MH thing. Okay, so what's going to happen is that we're going to get a K-theory class for C star MH. That's going to be our generalization of the index. Okay, so this slide is I'm supposed to talk about the proof of the propagation theorem. I don't think I'm going to talk very much about it. Let me sort of scoot through this, but the basic idea is that we use Fourier analysis. We relate f of d, the functional calculus of d, to f hat, the Fourier transform of f, together with these particular operators, e to the itd. These are the so-called wave operators associated to the elliptic operator d. Those e to the itd's can be understood by techniques related to hyperbolic equations, and in particular, we can understand how rapidly they propagate information. My example of Maxwell's equations was not just a made-up example. That's actually an example of what one of these e to the itd operators might be. And that means that we can relate the propagation of the operator f of d to the width of the support of the Fourier transform f hat. So as long as f hat is compactly supported, it turns out that f of d has finite propagation. Its kernel has finite bandwidth. So that's a key idea. I expect other people will explain that in greater detail. I don't think I'll go into that because I want to move along. What I want to do is to point out what this tells us is that if we're in the complete case, then the functional calculus just doing exactly the same thing as before. I mean, we didn't change a thing. That's what's so satisfying about this approach. We just do the same thing again, and just by magic, something interesting falls out. The functional calculus gives us a cycle, a C star of x. And the corresponding element of K-theory, we're going to call that the coarse index. It lives in Kn of C star of x. I'll say in a moment what n is. Okay, we have the operator, we have the functional calculus, we have the row algebra, they fit together, we get an index. If we're dealing with a compact manifold, let's just imagine we took this whole process and applied it by mistake to a manifold which was compact anyway. Well, then what would happen? C star of x in that case is, what do? We take the locally compact finite propagation operators and close them. Well, in the case of a compact manifold M, finite propagation doesn't mean anything. Every operator is finite propagation. Locally compact just means compact, because locally is everywhere on a compact space. So in the case of a compact manifold, C star x is the algebra of compact operators. The K-theory of C star x is the K-theory of the compacts, which is an integer. It's the group of integers. And what we recover is simply an integer, which is the ordinary index of D. So this machinery indeed generalizes the ordinary index theory to a non-compact case. And yeah, what is this n? Well, it arises from consideration of grading. Okay, what turns out to be the case is that the n is the dimension of M, the manifold, the underlying manifold, mod 2 or mod 8 if you like, real K-theory. Now, I mean, something interesting happens here. In the case of the classical index, if you have a differential operator on an odd dimensional manifold, a simple symmetry argument shows that there is no classical index that you can possibly have. But in the case of this non-compact manifold index, something interesting can happen for odd-dimensional manifolds. We'll see what it is in a moment. So there is the scope for index invariance to arise both in odd and even dimensions on all kinds of different manifolds. There's a lot of different space for indices here. Or to put it another way, this group, Kn of C star x, can be a very interesting group. It can contain a lot of things, and therefore we can get a lot of different possible index invariants. All right, so that's what the coarse index is, just as a matter of definition. But you might want to ask, well, what is so coarse about this coarse index? Why did I call it that anyway? What is the, if you like, what is the geometric content of the coarse index? And this took a little thinking about. You can write down the definition, but figuring out what it defines is another matter. But eventually you find the answer, and here is basically how it goes. Suppose I have a couple of metric spaces. And suppose I have a map, F, from one metric space to another. We'll say that the map is coarse if it has two properties. The first property is that the inverse image of a bounded set is bounded. And the second property, which is somehow the key one, is that for every r, there is an s such that the distance from x to x prime less than r implies the distance from fx to fx prime less than s. So this last second condition, the one I underlined in red, is one of those things that you would chastise your calculus students for writing. Right? You try and teach them a definition of continuity, and they write for all epsilon there is a delta, or for all delta there is an epsilon, or something like that. There are various ways of getting the definition wrong. This is one of the ways of getting a definition of continuity wrong, but it turns out to define something really interesting. What it defines is the idea that the map F does not expand things in a non-uniform way. Okay, so that if points in the domain are close together, then points in the range are relatively close together as well. And the key to this definition, the key to understanding how it works, is to realize that these quantities r and s should be thought of as large and not small. Okay, so that if 2 points x and x prime are within a mile, then their images are within 2 miles. If 2 points x and x prime are within 10 miles, their images are within 1,000,000 miles, something like that. That's the idea. That's what a coarse map is. And these maps, of course, form metric spaces, and maps like this form a category. And there are some natural equivalence relations, both on maps and spaces. You can say maps are coarsely equivalent if they're bounded distance apart, and spaces are coarsely equivalent if there are coarse maps going one way and the other way that are inverses up to this notion of bounded error or bounded distance. So the distance from x to g of f of x is bounded, and the distance from y to f of g of y is bounded. And it turns out that the computation of the K-theory of this translation algebra is functorial under coarse maps, and that coarsely equivalent coarse maps induce the same homomorphism on K-theory. So you should compare, for a sort of mental orientation, you should compare this K-theory of C star x with ordinary homology. You should compare coarse maps with continuous maps, and you should compare this notion of coarse equivalence with homotopy equivalence. If you do that, then you find that there's a strong analogy between this large-scale mathematics that we're doing here and the small-scale mathematics of homotopy theory. So, I said already, coarse equivalence is large-scale equivalence. The most classic example of this is the theorem of Milner and Schwarz from the late 50s, I think. If you have a compact manifold and take its universal cover, then the inclusion of an orbit gives a map from pi1 of y to the universal cover of y. So, all right, let y be the circle, then y tilde is the real line, and this is the inclusion of the integers in the real line. This is always a coarse equivalence, according to Milner-Schwarz. And in particular, all compact manifolds are coarsely equivalent to one another. And that's why all indices, thought of in this sense, on compact manifolds, belong to the same group, namely the group Z of integers, K of C or K of the compacts. Let me just make a kind of philosophic remark. One way of understanding the McKean-Singer formula is to say that it tells us the index depends only on G of D, where G is supported near 0. Okay, remember it said we could compute the index from any function just given that we know something about its value at 0. So if G is supported near 0, then G hat has support which is very, very large. That's the uncertainty principle. And what that means is that G of D is an operator of large propagation. So the index, this coarse index, depends on the properties of operators of large propagation. This is a conceptual way to understand why this particular notion of index is exploring the coarse or large-scale structure of M. It is tied in with the way the McKean-Singer formula works. Okay, so what have we done? We have, first of all, we talked about the classical index on a compact manifold. We sort of interpreted that in a K-theoretic way. Then we've shown that by introducing this translation algebra, which depends only on the coarse structure, we can make an analog of the classical index on non-compact complete manifolds. And what we've not done is to give an example to show that this analog is actually something interesting. It's completely imaginable from what I said so far that this analog of the classical index might always be 0 or might be always some trivial thing. So let me, in the last few minutes, sketch out one of the first examples which shows that this coarse index can be actually a non-trivial and therefore interesting index. And here we're going to talk about so-called partition manifold index theorem. So let's imagine, oops, I won't do that. Let's imagine that we have a complete, connected, oriented, I think I said enough words there, Riemannian manifold. It's partitioned, we'll say, if there's a compact codimension 1 submanifold, a hypersurface, which cuts it into 2 bits. So let me just draw a picture of a partition manifold for you, or attempt to. I have to draw my pictures very long and thin because of the limitations of this screen. Okay, so here's our manifold M. It's a surface with lots of little angles in it somewhere. Here maybe is the hypersurface N. And you see that N disconnects M into 2 different bits. Well, it's not at all hard to convince yourself that this notion of partition manifold is, at least in the world of coarse geometry, it's equivalent to having a coarse map to the real line. Sometimes I put absolute value signs when I want to remind myself that I'm thinking of the real line as a metric space rather than something else like a group. Okay, so what do? I just map the partitioning hypersurface itself to 0, and then I map everything else according to the distance function from the partitioning hypersurface, except I make sure to map one side to the positive side of the real line and the other side to the negative side of the real line. Then I have a coarse map to absolute eval like that. So a partition manifold, which is actually a very natural thing, which appeared in, for instance, Novikov's discussion of Pontryagin classes in the 1960s, things like that. Partition manifold, which is a natural thing, is related to this coarse geometry. And what that means is, let's get rid of this diagram again. What that means is that if M is partitioned, and if we have an elliptic operator on M, then there's defined a partition manifold index which lives in the K-theory of C star, not of M now, but of R, the real 9. Okay, and what is it? Well, of course, it's nothing other than the index which lives in the K-theory of C star M, or X, as I seem to have said here, mapped under the functorial map to the K-theory of C star of R. Okay, now the K-theory of C star R, well, that's just a single group. I mean, C star R is a big C star algebra, but its K-theory can be computed by a number of different methods. And it turns out that when n is odd, we get the integers z, and when n is even, we get 0, at least in the case of complex K-theory. So what that means is that this partition manifold index is providing us some new integer invariant. We have an odd dimensional manifold. We have this extra geometric structure of partition. What comes out, using this coarse geometric machinery, is an integer. And of course, it's natural to ask whether there's an index theorem, like the Atiyah-Singer index theorem, which is actually going to compute this integer for us. Well, it turns out that there is. And the answer is that in this situation, the index, the partition manifold index of D, is the same as something which can be computed by the standard Atiyah-Singer index theorem, the ordinary index of the restriction of D to the compact manifold N. Let me very quickly just draw a picture, just try and explain what I mean by that. So the blue is M, the green is N. N is an even dimensional manifold, so what we need on N is a graded vector bundle for some Dirac type operator to act on. How do we get it? Well, we take the vector bundle S, which we already have on M, we restrict it to N, and then we take the unit normal vector field, because of the various orientations, and let that act on S via Clifford multiplication. It acts as an involution. That involution defines a grading. That's the structure we need to talk about the restriction of D to the compact manifold N. But if that doesn't make any sense, don't worry too much. That's just a little linear algebra bookkeeping. So what we've done is we've equated the index, one kind of index with another, and actually that's how the Atiyah-Singer index theorem always works. When you boil it down to the details, how the Atiyah-Singer index theorem works is that you start with some standard operators, some class of standard operators, and then you show how you can compute the indices of other operators in terms of those standard ones. So this is completely in the pattern of a standard version of the Atiyah-Singer index theorem. So that's our partition manifold index theorem. There are now a bunch of different proofs of this which use a bunch of different ideas. I will not run through this proof because I only have 2 minutes left. But I just want to say what the consequence is, and I think that's basically the theme of the whole conference. The final consequence is that the geometry of a partitioning manifold, that is, large-scale geometry of M, can be combined with analysis using operator algebras to say things about, sorry, I said that wrong, the geometry of the partitioning manifold, the sort of classical index, can be combined with analysis, that is, operator algebras, to say things about the large-scale geometry of the partitioning manifold N. And there are a number of cute applications even of this theorem, which I don't have time to explain right now. But in my next talk, which is on Thursday, I will pick this idea up and we will sort of take these, what are called primary index invariants, which I've been talking about up to now, and see how we can develop them into more sophisticated secondary invariants which measure, as it were, the reason why two primary invariants agree with each other. So that's the idea for what we're going to do on Thursday. But right now, it's time to stop, and in Germany, it's time for refreshment. Here in Penn State, we still have a whole day's work to do. But thank you very much. If there are any questions, I'll try and take them.
Maybe just to clarify a
question.
point for myself.
Can you?
Okay, let's have a German question.
Could you have one of Philip or the other person repeat the question? It's a little hard to hear.
Yeah, so I think the question was how common are partitioned manifolds, is that right? Sorry, the...
It's coarsely equivalent to a disjoint union of two.
Right. So it's the question is it coarsely equivalent to a disjoint union of two things? If it's is that? Mm-hmm. Yes. So I maybe I'm. What exactly is the question, though? Sorry, I'm. Sorry. Yeah, so
How common is it? I guess this is
I guess the question is how common are partitioned manifolds, and it seems maybe it's a restrictive condition because it forces you to be coarsely equivalent to something which is disconnected or which has more than one end in a different way.
Well, certainly a partitioned manifold has more than one end, but it's not an awfully uncommon condition in that anytime you have a Z covering of a compact manifold, then that is a partitioned manifold. So there's certainly plenty of examples of such things around. On the other hand, I would emphasize that this is only an example. It's not somehow the whole story.
enough.
Okay, by the way, hello, Rufus.
Yes, hello, John. Very nice to see you.
I could only see half of you before, but I just got a glimpse of, that's right, the whole of you. All right, thank you. Was there another question, Michael?
Remind me a second one, Germany.
I'll squeeze mine in. Yeah, so regarding coarse maps and what the definition captures, for your example with the partition manifold, I could easily imagine some kind of like two horns stuck together where the level sets of equal distance from the compact submanifold get very, very large, so that your map down to R takes things that are very far apart and crushes them to points which are at distance 0.
Yep.
But this is exactly the sort of thing that a coarse map does not care about. So
Yeah, that is still legitimate. That's, you know.
So you can have things, coarse equivalences can crush very large distances to small distances. And this
Not coarse equivalences, but coarse maps.
coarse maps. So you have a coarse map to R, but not a coarse.
I'm not saying we have a coarse equivalence. And the picture that I drew had a coarse equivalence to R, so maybe that was confusing. But in general, all I claim is that there is a coarse map.
There's a coarse map. Okay.
It was a coarse equivalence because of that long, thin box I had to fit it in, I think.
That was the whole question.
Any more questions?
Yeah. Oh. Yeah, we have a question here, I think.
Yeah.
So in the beginning of the lecture, there was the definition of the spectral picture of K-theory, where maps from C0R with the grading to the complex of Hilbert A model. Now, in the case of the C-star row algebra, you take the functional calculus map, and I would like to know what the Hilbert C-star X module is in that case.
Did you hear that, John? So the question is, you have your spectral picture of K-theory, and you're meant to get a map from C0R into the compact operators on some Hilbert C-star A module. For the case of the row algebra or the translation algebra, what is the Hilbert A module?
It's the algebra itself.
Thanks. So maybe to clarify on that, the compact operators on just the thing as a Hilbert A module over itself is the C-star algebra itself. So.
Sorry, I should. All right, I was just going to say that, but Rufus said it already, so.
Sorry.
Okay. Okay. So we'll repeat on Thursday, hopefully at the same time.
Oh, there's one more question.
I hope you guys have a wonderful time over there in Freiburg.
Maybe. Are we allowed a question? Maybe.
Yes.
Hey. Okay.
Yeah, so I understood that the operator FD itself is not necessarily compact as an operator on a Hilbert space. So it is compact in this setup, or how do you make that work? So the functional calculus applied to the operator D would give something of finite propagation, smoothing operator, but not necessarily compact, isn't it? Mm-hmm.
Yeah. So right. Okay. So the question was, if you're in this non-compact setting and you apply your function f to an elliptic operator D, then f of D will not be a compact operator. It will only be locally compact. So how do you make that work?
Can we clarify the question? I mean, everything you said is true,
Yes. I think the answer maybe partly is I can clarify the question by trying to answer it. That you don't need something compact. The idea of taking an index in the K-theory of this row algebra is, well, you don't get an integer anymore, but you get an element of this abstract K-theory group, which is
so I would have to know what those compact operators on the algebra actually do, yeah?
Yeah, so
okay.
You would need to have information about the K-theory of the row algebra to say.
But we had this
something.
answer before. The compact operators on
Yeah.
the algebra as a module over itself is the algebra itself.
Yeah.
So everything is compact.
Yeah, so compact in the sense of Hilbert module theory. Yeah.
Okay.
Yeah. Sorry, we're now having a conversation amongst ourselves. We'll stop now.
Okay, I think I will say farewell because I know
Sorry.
classes to teach and stuff like that. Yeah, it was good to talk to you and enjoy the rest of the conference. We'll see you on Thursday.
Okay, thank you very much, John.
All right.
Okay. Okay.
Thank you very much.
Sorry.
See everybody. Lecture.
No, it's necessary to disconnect.
Throwing in this compact one word into the monastic group, make this operator as soon as it so the compact is relative to the basic algebra. So if you take the basic algebra and you blow it by our instant matrices, somehow two-dimensional, then you have to put in a compact condition. If you don't, you just take the algebra itself, and the one by one, and it's the smallest possible, that's compact enough. So now I don't know what P of H, P inside P of H, so H is our L2 of
it.